Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So let me just maybe briefly introduce Boris. Actually, I first met him while visiting Oxford. That was July or something like this. Yeah. He sounded to me like he does interesting things. I said, why don't you come and give a talk? And to my understanding, he does like theory, some very deep theoretical stuff, but as well he does coding and very low-level coding. So let's see. I have no idea what's going to be.
Okay. Shall I start, or is this okay? Okay. So hello, everybody, and welcome to my talk. Thank you for giving me the opportunity to tell you a little bit about my work. And my work is in the area of semantic web, ontologies, and RDF. And there has been a lot of talk about it, so I won't give you the standard introduction of what semantic web is. I'm going to actually do this by presenting you two applications, real-world applications that I worked on in the past that use these kinds of technologies. And then I'll introduce the actual technologies later. So in 2009, I did a 3-month project with a startup from Barcelona called Incremental, which got bought by Skyscanner, and for which I developed a bit of semantic technology. Now, what this company wanted to do, they wanted to improve search and tourism domain. And in particular, so far you have Expedia, for example. You have to know exactly where you're going. You have to, and you have a very simple form. You have to fill that form out, and what comes out comes out. Their idea was to do something more advanced. So, for example, because they initially did it in Spanish, so this is in Spanish. This means hotels close to the Colosseum in Rome, essentially. Now, if you did this, if you tried to solve this query using Google, you would get all sorts of random stuff because as you know, Google would simply match keywords, hotels, Colosseum, Rome, so you might actually get the Wikipedia webpage about Colosseum and that kind of stuff. But this is clearly not what you want. You have to understand this query. Now, there is clearly a natural language layer here, which I wasn't involved in. This is not my field. But once when you actually understand this, and actually they developed quite a nice solution for this, by the way. Once when you understand this query, what then you need in order to actually give the results, you have to have a database of facts, Colosseum, Rome, where is what. You have to know that, for example, not just geographical, but you have to have background knowledge about the whole domain. And for that, they needed a way to represent large amounts of heterogeneous data. Clearly you could stuff all this into a database. And in the end, actually, there is a Postgres database at the back end. But there is a semantic layer in between which makes these things a little bit simpler. And I'll show you a bit later how this is done. And another very important thing for them was inference. So, for example, if you have a query for accommodation, that should include hotels, bed and breakfasts, and all that kind of stuff, which you can automatically infer from the data that you've got in your database. And this is clearly not something that you can do with just Postgres. Another application, so this was more a research application, which we did with Samsung from Korea, but with the research department. So what they wanted to do is they wanted to use sensors on mobile devices like Wi-Fi, GPS. You've got a lot of different sensors in the phone to provide context services, context-based services. So what is a context? The context is, for example, at home, in a shop, with a friend, that kind of stuff. And then you want to adapt the behavior of the device depending on the context. So, for example, if you're close to a friend who has a birthday, which is your context, then there is an action, remind the owner of the phone to congratulate birthday. Now, clearly you could do this in Java. You could just hard code all of these things, like if this, then that. But this is very inflexible. So the idea of Samsung was to use semantic web technologies to describe what are those contexts and to describe the adaptations declaratively using technologies that I'm going to introduce shortly. And then they used an inference engine. So this was like a small in-memory engine that I actually developed and that ran inside their phone that then could interpret this data coming from the sensors and actually decide what to do in a particular situation. So those were the two motivating applications, and now I'll go into how do we go about solving them. So the first thing you need is a data model in order to represent your data about tourism or your data about contexts. And in particular, people developed this data model called Resource Description Framework. This is quite closely related to, so this grew out of the research on semi-structured databases from the 90s. It is also related to the research in graph databases. So it's kind of a graph-like data model where you have various nodes, and this is like a simple graph here where you have the node representing some person called Peter, a course, Intro to AI, Oxford University. I mean, I think all of this is fairly self-explanatory. But then, just to fix a little bit of terminology, so you have nodes, which are sometimes also called resources. Then you have these labeled arcs, which are sometimes called triples. So I'll use this terminology throughout the talk interchangeably. And what is also quite important is you have these special arcs. So for example, RDF type is a built-in arc which says that Peter is an instance of a class called person. So unlike in a database where you have your schema and the data separate, in RDF it's all bundled into one big thing, and then you use these special edges to denote that. And for example, you have another special edge here, subclass of, for example, saying that professor is a subclass of employee, which is a subclass of person. And now these special edges have a particular semantics associated with them. So what I can do is I can run reasoning, and then these red links are the ones that you can infer from the explicit data. So this is the very simple stuff. So if Peter is an instance of class called professor, and professor is a subclass of employee, then Peter is an employee. And then also you can infer, transitive closure of the class hierarchy. I mean, those are very simple examples, but you can do this much more complex. I mean, obviously I can't do this all on the slides, but for example, in this experience scenario, they used quite a lot of these kind of inferences to infer what is near, to define actually what is near to what and that kind of stuff. So this reasoning is something that actually differentiates the semantic web technologies. It's a key aspect of semantic web technologies compared to just plain relational databases. Now, in order to actually capture, so we have this data and we want to capture these rules of inference formally. For that, we can use a well-known formalism from databases called data log. Actually, it's not just databases, both databases and AI. I mean, this is one of the most well-known formalisms out there that's been used in various contexts. So I'll just fix a little bit of terminology. I mean, I won't have a lot of definitions, but I just need some terminology. So you have these constants, which I won't go a lot into that. In RDF, these resources or constants, all of those are synonymous, are identified using URIs, and this allows you to create these well-known vocabularies. So for example, you could create a Microsoft ontology where you would then have a URI representing the product class of Microsoft. I mean, obviously, this is soft in a sense, that soft benefit of semantic technologies in the sense that there is nothing fundamental about this. Just use a internet domain prefix, but it's quite useful in practice. Then you have terms which you can have these constants or variables which are written like that, although sometimes I will omit this question mark and I will use X, Y, and Z for variables. And then what you can do is you can build atoms, which are of this form here. So you have some n-ary relation, and then you have some terms here. Now, this, I hope, won't confuse you. So when you talk about triples, there is just one relation called triple, basically. So we usually avoid this R, and instead of round brackets, we use angle brackets. So this triple relation can be embedded into the RDF can be embedded into the relational model using a single ternary relation. And this is actually how you can store RDF data in a database as well. But that's not the only way. So what people sometimes do is if you find this S RDF type O, so these kinds of triples you store in a unary relation, O, and then you just store the subject in that. And then if P is different from RDF type, then you have a binary relation which connects the subject and the object. So throughout this talk, I will flip between these various ways of looking at RDF. And I mean, in the literature, this is a bit, jumbled. You have to know exactly also where a particular paper is coming from. But okay, however, I can have, atoms of this form, or atoms of this form, or atoms of this form. It doesn't really matter. It's all kind of the same thing, that the underlying technology is the same. And then what data log is it's a bunch of implications of this form, and this essentially means whenever you can instantiate the variables in this B1 to Bn, you then derive whatever follows from the head. And then a data log program is a finite set of data log rules. And then this is the main thing of the main point of this paper. So how do you do reasoning in data log? There are various different possibilities. One is to do materialization, which essentially means before you actually go and do anything with your database, you run a pre-processing step in which you apply these rules until you reach a fixed point, so until you basically derive everything that you can derive. You store all that in the database, and then you can just query the database as and when queries arrive. I mean, obviously this, there is a cost increase in memory. The question is how long it takes. All of these things I'm going to talk about a bit more later. But the fact is that this is not just academic, actually. This is done, for example, in Oracle system, in quite a lot of commercial systems. It turns out that this memory blow-up is not that bad. And also there are techniques to actually not maybe materialize everything, but I won't go into that in this particular talk. Yeah?
So first, two questions, and they might be addressed in the talk later on, but one is all this is sort of deterministic, right, where the relationships are deterministic. If we have probabilistic sort of atoms, you might not know, you might have a probability that some, like a hotel is a luxury hotel, right? So there is a probability that the hotel is a luxury hotel, and there is also this other issue of context. According to this particular website, this hotel is a luxury hotel, right? And some other website might contradict this other website. So how do...
I won't talk about this in this talk, but for example, there are probabilistic extensions of data log. How it exactly works, I'm not actually an expert in probabilistic data log, but I just know that there are. So roughly what there happens is you basically make your rules encode some Bayesian network, basically. Then your facts are inputs to this Bayesian network, and then the evaluation of data log rules corresponds to, your typical kind of, inference problem with Bayesian networks. But, I mean, you don't need non-deterministic computation for that. It's still, deterministic in a sense. It's just that you work with probabilities. You annotate each fact with a probability. What was the second thing?
The second question is about contradictions.
Yes. So what you can do is, I mean, it's all a matter of encoding. So, for example, what you can do is instead of using a ternary relation, you can use a forary relation. And actually in RDF, there is this notion of named graphs, which basically assigns this fourth category to each triple, which essentially can be then used to encode any different kind of context. There has been also work on, getting more structure into this context information, so you can have a lattice of annotations, and then there are some rules on how you propagate these annotations during inference. So all of this is done, but it's not the topic of this talk. The topic of this talk is to actually just do this materialization. Just for your, just so that you see, so what you can do with data log is you can encode these inference rules. So for example, what I actually showed on that slide before can be encoded like that. This is just one way of doing it. And here I'm using one fixed data log program. I could also extract the schema and then create a program based on the schema, but it's all kind of the same thing. I mean, it doesn't really, the details of that are not necessarily important. So what is the goal? Okay, all of this is just, the background. What is the goal of this talk? The goal is to develop techniques for materialization of data log programs on RDF data. Now, I'm going to actually refine this a little bit because we looked a bit into some of the trends in database systems, and there is a big trend towards, first of all, main memory systems. There were some statements even that databases will end up in main memory. I mean, just recently we bought a 256 gig server for less than £5,000. So, you can store quite a lot into 156 gigabytes. So, and I mean, because this is such an intensive process, main memory makes things much easier. So I will focus on main memory techniques, which means that I will, for the most part, assume that random access is cheap. I know this is not the case, caches and so on, but it's much better anyway than on disk. And then another thing is materialization is computationally intensive. So, but already this laptop here has 4 cores. This server that we bought has 16 physical cores and 32 virtual cores via hyperthreading. So I'm refining my goal here and saying, materialization, but in main memory multi-core systems. And we've developed a research prototype called RDFox. So it's not RDFox, but RDFox. And you can download it and you can play around with it. Okay, so I will start with describing this algorithm for parallel materialization. And before I do that, obviously, I should tell you a little bit about how this is done. I mean, obviously, we are not the first one who came there and said, oh, let's parallelize this. So there are generally 2 different approaches to parallelization. One can be called inter-query parallelism, which essentially means that, all of these rule bodies correspond to queries which you have to evaluate over your data. Now, if you can show that 2 rules are independent, then you can run these queries in parallel. But the problem is that in practice, you don't get that many independent queries very often, so your potential for parallelization is limited. Another possibility is intra-query parallelism, which means that you parallelize the evaluation of a single query. And there are, well, at least 2 ways to do that. One is to partition rule instantiations to threads. So what people sometimes do, let's say you have some variable x and you have n processors, and let's assume, as we will see quite often, all of these objects are encoded as integers. You use some dictionary encoding. So this is actually, it makes sense. So what you do is you constrain rule bodies using an atom of this form, x mod n equals I, and then and then you basically say, okay, on thread 0, I is going to be 0. On thread 1, I is going to be 1, which essentially means that you now evaluate your query, but you basically handle only certain rule instances on different threads. The problem of this kind of technique is that it is susceptible to data skew, because there could be more of these x's which mod n go to 1 rather than 5, for example. And then, for example, what you can do is you can also parallelize joint computation. There has been a lot of research in the database community on how to do that efficiently, even in main memory. But the problem here is that, well, I don't actually believe that this is, as you will see later, this is that relevant, simply because you have this data in memory, you have it indexed. Quite a lot of doing this main memory hash join is about actually indexing the data. Whereas this is not the most efficient way of doing it if the data is already in main memory and already indexed, basically. So while it can be parallelized, I think you're still doing way too much. So what we want is actually a technique that will distribute workload to threads evenly and with minimum overhead. So that's my main goal. And one other thing which is quite interesting here is that, and that's actually something that really hasn't been considered in databases so far, and that is that, well, first of all, to evaluate these queries, I need indexes. And this is simply because, as you know, like if I just run a query over the whole database, it's going to take forever. For example, because there can be many ways to infer a triple, I need to do duplicate elimination. That's critical. Otherwise, this algorithm, this bottom-up computation, is not even guaranteed to terminate. So I can't say, oh, I'll index it at the end, actually. I have to do this as I go along, basically. So now there has been a lot of work on indexing RDF data, but mostly this is assumed that the data is static. So you can, sort your data. You can apply very efficient sort-merge joins. All this is great. But the problem is that here, you're actually interleaving query evaluation with updates, because you're evaluating this query and then you're adding new data all the time. So these assumptions that people actually used in databases are no longer hold, basically. So what we need is we need a data structure which supports indexes and efficient parallel updates. And that's a combination which I think is somewhat unique in this work.
Yeah. These updates, are they new facts that
yes.
That are coming from the external world, or
no,
or
that
the
you
inference
infer,
itself?
actually. So I'll give you an example just now. So I've actually outlined this idea. So we have this problem. First, how to distribute computation to cores. Second, how to index data. And I'm going to now talk about these two different aspects of the problem. So the first one is this new algorithm, which is actually quite simple, that we developed. And I'm going to first present it as if everything's running on one thread. And then I will show you how we can actually efficiently parallelize that. So let's assume that this is my input database that is given. And this is the only rule that I need to materialize. And now I need to do this materialization. So this is essentially what I will do. I will first assume that my data is ordered. That's why I drew it actually like this. So there is an implicit ordering from top to bottom. So we actually do store data in arrays rather than sets. And what we do is we essentially extract an atom from this table. And we now try to find, we try to shove this atom basically into this rule, match this one body atom in all possible ways. And when I do this here, so X goes to A, Y goes to B, and I get a subquery A of A. Okay? Now, what I do is I evaluate this subquery in the data. And you might say, OK, A of A is here, so let me derive A of Y. But this is actually not good, because when I reach A of A, then I will put this A of A here, and then I will match this again with RAB before. So there are two ways to satisfy this rule. Once you start from R, the other one you start from A. That's why when we do these matches, we do the matches only with respect to the facts that are above the current fact. And because this A of A is below the current fact, we don't do anything. We simply skip over this potential match. The same thing, RAC, the same thing happens. Current subquery is A of A, RBC, and so on. And then finally, we get to A of A. We now stick this A of A here. We get a subquery called RAY. And this Y can now be mapped to the fact above. And I derive new facts AB and AC. This answers your question. So those are the facts that you actually produce during this computation. And you simply just continue. And then when you get to the end, you're essentially done. What this does, it essentially encodes a well-known algorithm from databases called the semi-naive technique, which ensures that you consider every rule instance only once. This is important because this number of times you consider a particular rule instance, that's the determining factor of performance in this whole setting. So OK, this was very simple, actually. Really simple with this proviso that you map these subqueries only to things which are above your current fact. Yeah?
This seems like quite computationally expensive, right? If you have a huge sort of table, every time you come to a new fact, you have to explore, you have to...
well, for that you need indexes.
Yeah, OK.
For that you need indexes. That's precisely why I need indexing. I'm not going to explore the whole table. Okay? I'll get to that. So, OK, how do we parallelize this computation? Well, the whole point is that I can extract these facts independently, actually. So I can let one thread extract this fact, one thread extract this fact. They can consider these subqueries independently because this part above the current fact doesn't change. The new facts come always at the end. And you've actually decomposed this huge problem into a large number of subproblems, which are fairly small, evaluate this subquery, basically, which you can very efficiently distribute to different cores. So there is no need for thread synchronization, only actually when they reach the end of this table. Then it could be that one thread extracts one fact, and the other thread has nothing to do, essentially. But what we've noticed is that the threads are, until the last final milliseconds, essentially, are equally used, basically, simply because there is no need for them to actually do anything with each other.
But the threads need to be synchronized, right?
No.
OK, so suppose there are 4 threads.
Yes.
and there are 4 sort of properties, 4 rules they check, and the thread finish and basically add 4 more sort of properties, and this guy needed access
Yes, only at the end, because you see what usually happens is that, you have, let's say, millions of facts, right? And you start at the beginning. So, these new facts are written at the end, but there is still this million facts in between, basically, that the other threads can actually process independently. That's why so only at the end, when all threads are reading stuff, at the very end of this table, then there is a synchronization step there. But it happens only at the very end. And actually, here is an example where this algorithm completely fails. So you have, again, the same rule, but this encodes a line, basically. So now what you get is, you will extract A of A, shove it in there, you will get A of B, and now you actually process that fact to get A of C, and there is nothing that the other threads can do, essentially. But this is a very pathological example. I should actually say this is a linear rule, which means, so it can be parallelized in theory, but we've looked a lot into trying to make this theoretical result work in practice, but it's just actually one of those things where I firmly believe it's absolutely irrelevant for practice because of the number of processors that you need to make parallelization pay off is something like cubic, basically. So, although there is a disconnect there. On this particular, example, you will get this pathological behavior, but we actually haven't seen that in practice ever. And there is very little need for threads to synchronize here. So this was the first part. Yeah, go ahead.
Do you assume that you evaluate each rule independently of the other, so one at a time, or can you use threads to evaluate more than one rules at once?
I could, but actually, so this was the natural way of parallelizing this, in my opinion, simply because you have this one fact. This usually matches to a small subset of the rules, because you have this R, X, A, B, basically. You just find the rules which contain R in this thing. And that gives you a small number of rules, which then you all evaluate in this one thread. We didn't actually see the need to, then parallelize that in particular, because that would then require some form of synchronization between the threads. But this was good enough, so to speak.
I guess it depends on the number of rules, right?
We had actually situations with like hundreds of thousands of rules, and it still worked really well, actually. Simply because, I think this is simply because the number of facts is much larger than the number of rules. So because of that, the number of sub-problems that you get is, again, much, much larger, basically, because each of these facts corresponds to one sub-problem. So that's why I think this is a better way to parallelize it. Go ahead.
Create rules as you go on dynamically?
Well, that would be more difficult, obviously, because, for example, we have to have rule index as well. So to find, in these cases where we have like these 300,000 rules, you don't want to scan sequentially the rules. So yeah, that would be a major nightmare, actually. So rules are assumed to be static, although I will get to one point where they do change a bit, but that was not easy. Yeah, go ahead.
The way I was imagining this is basically materialization would happen once, right? You have your facts and you have your rules, and then materialization would happen, yes. And then you have got your thing. Now you can do queries, right?
Correct.
So in the real world, basically a lot of facts might keep on being added.
I'll get to that. There is incremental updates. We developed a new algorithm for that. That's at the end of the talk, and I don't think I'm going to manage to get there. But, we did some work on that as well. But however. So okay, the next thing is, we now have this. So as everybody here noticed already, we need to have these facts indexed. And actually, the main synchronization point, so when we started this, we were a bit naive. We thought that this algorithm was the best thing since sliced bread. But actually, no. The algorithm doesn't really tell you much, simply because the synchronization point was writing into this table. So you have this common data structure that you need to keep updating all the time. And doing that is, in my opinion, actually the biggest novelty. And this involves, to an extent just engineering, but also a little bit of conceptual thinking of how to organize this data structure that keeps kind of being attacked by all these threads at the same time. So what we roughly did, so what is the requirement? I mean, we have these RDF atoms, and we have these three terms, T1, T2, T3, some of which can be variables. And now what happens is during this query evaluation, you get a term which contains variables somewhere, and you want to return basically all the facts that match this partially instantiated atom. So that's the setting, basically. So how do we do that? Well, so you have 8 different patterns, obviously, because something can be a constant or a variable. You have 8 combinations. One possibility is, for example, you organize each triple into 3 singly linked lists. So, for example, the SP list collects triples with the same subject, and then within that list, the triples are grouped by predicate. Why is this useful? Well, if you have a pointer to the head of that list, well, you have all the triples which match subject, variable, variable. And then, because the triples are grouped with this subject predicate, basically, you can also use the same sublist for, if you have subject, predicate, variable, basically. And then you can do the same with PO and OS, and you've actually covered all of these 8 combinations. Now you need also indexes into these entry points. So you need IS index, which will, given a subject, give you the head of the appropriate S list. And then you have to have an ISP index, which, given a subject and a predicate, gives you the head of the SP sublist within this big list, essentially. And then you have also other indices for these other 2 lists. And you finally have to have an ISPO, which is essentially a big index that indexes everything for SPO. And that's actually very crucial, because you have to have this duplicate elimination. You have to eliminate these duplicates eagerly. Now, there is a small optimization here. Binding patterns of this form are rare. So what we do is we actually, in the implementation, use an SP, OP, and P list, which eliminates essentially 1 index. And then to answer patterns of this form, we use either IS or IO, depending on the size of the index. So just a small optimization. And this is what it roughly looks like. So you have this big table of triples. This is something, so everybody does this in RDF. So you use a dictionary encoding. You basically replace all resources with integers. For that, you use some kind of hash table somewhere, essentially. We do this by using small integers, not some randomly generated integers. This allows us to actually use these integers as array indices. And then, these triples arrive here in this table in whatever order, and you have the next pointer to the next triple in the same group, and you have your basically pointers to the start of a particular list. This guy here is an array. This guy here is a hash table. This guy is a hash table as well. Okay, this was all fine. This also was there quite at the beginning of our work, but it was still quite a pain to make it work really well. And why was that? Simply because to update all these lists, it's non-trivial. You have all of these threads. You have to ensure some kind of you have to ensure consistency, basically. And you have to do it in such a way that 16 threads actually make progress. They don't wait. So we went for like a round and rounds and rounds of different possibilities. And what we then actually found out is that, there is this idea of lock-free programming. So, okay, I assume everybody here is familiar with lock-based programming. So what you do is you have a shared resource, and you simply you simply have a lock. You lock this resource, and one thread has access. Then when you're done, you unlock it. Everything's fine. This ensures linearizability, which is this one abstract property that you want your system to have. It makes programming easy comparatively to anything else. But the problem is that these kinds of systems are susceptible to thread scheduling. So, for example, if one thread acquires a lock and then dies, fine, okay, then you can say it was a bug. But what if the thread gets swapped out? Because you hit something and then like the memory has to come from secondary storage. well then actually all the other threads are still being hindered by this one thread, essentially. And this is a problem when you have lots and lots of threads, basically. It can lead to this priority inversion, which means that, for example, if you have a higher priority operation, that still has to wait for lower priority operation to actually finish. Because of that, people have looked into lock-free programming. Now, the definition of lock-free programming is that at all times, at least one thread makes progress. I mean, so you can't say, okay, there are no locks, so it's lock-free. I mean, this is the actual definition, because obviously what is a lock? You'd have to define that somehow formally. These guys are usually implemented using compare and set instructions. So what is compare and set? You give it a location, you give it an expected value, and you give it a new value. And that's like an instruction in the processor. Every modern processor has something like that. What the processor will do is will go to this location, read the value. If that value is equal to expected, then it will write the new value into that location, and it will return, in all cases, the old value, essentially. And all of this is done in hardware, let's say by locking the system bus, for example, on x86. Just to contrast this, there is also notion of wait-free programming. This is not what we're doing. So wait-free programming is essentially when a thread is guaranteed to complete every operation in a finite amount of time. I mean, that's quite difficult to ensure, as you can imagine. In this case, one thread could, be delayed forever because, it does a cuss, it does a cuss, it does a cuss. There is no guarantee that it will eventually, finish. But, it's not really an issue. And then the other thing is that doing systems so that they're fully lock-free, that can be actually quite expensive because in some situations it just doesn't pay off. So we invented this moniker, mostly lock-free, which essentially means that for the most part, we are lock-free, but in some cases we resort to short-lived locks. So I'm going to now demonstrate how this works. And for example, because we use these linked lists, I'm going to start with a simple example. So you have this linked list here. Those are my triples that are already there in this big table. And now you want to insert these new, so two threads want to insert in parallel these new two triples in this list between these two guys. So how is that done? Well, both threads essentially say, okay, you are my next guy. Both threads do a cuss into this location here. They say, update, so this thread on the left says, update this to here, provided that your previous value was this guy. And the same happens on the other thread. Now, hardware makes a decision, and let's say that the thread on the left succeeds, and the thread of the left is happy and goes on, does whatever it wants afterwards, but the thread on the right is not happy, and the thread on the right has to now repeat the process. Now, it still wants to add stuff behind this guy, so what it does, it now actually modifies this here, does a cuss. Now there is no other thread contending, basically. The cuss succeeds, and it's all fine. It's a very simple idea, but the fact is that you don't need any kind of locking, and that turns out to be much more efficient in practice.
Is this not a spin lock?
Pardon?
Is this not just an implementation of a spin lock?
It's not a lock, no, because you see, there is no locking here. There is no locking because at any point, at least one thread will succeed entering this thing into the... So for example, let's assume you go here, and now this thread dies. Okay, fine, it died. This will never get inserted. Fine, that's a different problem, but this thread can continue. So it's not a spin lock. Does that... Because you see, neither thread ever did any action that would prevent the other thread from completing things. Spin lock would be if, for example, you had here some kind of flag saying, oh, let me lock this guy here so that I can write into this location here. That would be a spin lock. And then, let's say that this thread acquires the spin lock, dies, well, everybody else is stuffed, basically, because they can't acquire the spin lock until this thread resumes. Whereas here, there is no such thing happening. And another thing is hash tables. So we have these large hash tables. They're implemented, actually. We don't store keys inside the hash table buckets, but we just store pointers to the actual triples inside these hash tables. And let's now assume that both threads, we have two threads, they both want to add 136 triple to this hash table. Okay, they both hash, this triple, get some index. They both see, oh, it's not, we use here open addressing, essentially. So they both say, okay, this is not, the triple, so we need to scan this forward. Now, the problem is that here we do use a very short-lived spin lock, but I will later show you how we actually avoid this in most cases. So what now happens is both threads have found a bucket, and both try to lock it, and let's say that the left thread succeeds. The left thread now basically adds this triple, writes down the pointer to that triple, and the right thread sees that, oh, it's already there, so I eliminate duplicates. Now, this was a spin lock. The reason why I had to do a spin lock is simply because I would need multicast in this case. So when I was at this point, so there were two threads now poised to actually occupy this one bucket here. What I had to do is I had to allocate fresh memory to hold this triple. And then, so this essentially means I would now have to modify these three locations. I would have to modify this location all atomically. Now, there is this multicast, which can be simulated using single cast, but in practice, I really don't believe it's worth the bother. Yeah, go ahead.
If you have like a Haswell machine, for example, you can use hardware transactional memory to do that.
Yes, but I don't have it. This works on Intel, I know, yeah. I was like, please, just give me that, But unfortunately, it doesn't work like that. So there was a small spin lock here. Not so bad, because I will show you that we actually eliminate this spin lock in most cases. Another thing that, fine, okay, so this also is something that we did, and the system then parallelized much better. But then another thing that now happens is you have to take into account modern architectures. So when a core writes to memory, it does so via the CPU cache. Now, if two cores write to the same location, even if they use these, fancy instructions, casts, and all of that, you still actually have to synchronize the cache of these caches are independent. You have to synchronize them. So what usually then happens is, the one thread actually has to write down, whatever it had in its cache, and then, the other thread can now write into that location as well, and then, the other thread can load it. So there are these cache coherency protocols. I mean, the whole point is that at the hardware level, if threads actually keep writing to the same location, you will get a very slow system which won't scale very well. And in this situation, we have, well, at least three such bottlenecks. So one was this pointer to the end of the triple table, right? Every time you add a triple, you increment that pointer. Every thread writes to that single location, which essentially means that every thread keeps kind of thrashing other threads' cache. Another thing is pointer to the next triple to process. That's as well. So, every time you increment that pointer, you are thrashing other threads' caches. And then, in these ISP, IOP, and P, you have these entries for SP, OP, and P. Some OP combinations can be quite common. So, for example, something is of type person. That's going to have the same entry, like every person is going to go into this same entry. And every time when you derive, X type person, you will be writing into this place. So all of this actually made the system still not be actually there where we wanted it to be. So okay, to address one, what we simply do is we amortize this. So instead of extracting triples one by one, we extract a window of, I think, 1,000 triples or something like this. So you essentially pay, I mean, you still have to have synchronization, but you amortize it by, doing it in bulk. To this problem of writing, we solved in a similar way. And what we actually do is, for every thread, we reserve some space in this big table in advance, again, in blocks of 1,000, I think. And then let's say that both threads now want to add 132. What they can do now is, first of all, because this is now private space for both threads, they speculatively add this there. Okay, and both of them do this at the same time. And now they both, compute this index. But now there is no problem, which I outlined on the previous slide, simply because this is there. I know exactly what the address of that is, and I can just cuss into this. No spin lock needed anymore, simply because this memory allocation has been done in advance. Okay, what happens with that? Well, more triples will be produced, so this guy can actually reuse this space for the next triple that it needs to insert. And in this way, you make triple insertion fully lock-free, essentially. So there is just one other place, where we use locks, but, it's just very small corner case as well. And then the third thing was, so if you remember, we had this problem, common groups always went to the same place in memory. Well, what we do is essentially, we have this global ISP index, but we also keep indices per thread, which keep addresses which keep their private insertion points. So, there is this one list here, which goes from this triple to this, but every thread actually uses a different triple in that list as its insertion point. So this essentially means that actually, this is even better because this insertion point is now private to thread 1, you don't even need to use these cus instructions, actually. You can simply write it into memory and rely on, simply just atomicity of memory operations of the processor to actually do this. So with all of that, we were able to achieve this. So these are different, data sets. I won't go into where we extracted them. They are fairly commonly found in the data in this community. This was a machine with 16 cores, 16 physical cores, 32 virtual cores, and actually we got pretty decent speed up. So the speed up, for example, for this Claros data set, which was the best, was on 16 cores, it was 13 point something, which is, I think, fairly decent. I mean, you will never have a speed up of exactly, 1. And then even with these virtual cores, you still got a speed up of roughly about 20, yeah?
What is the y-axis?
The y-axis is the speed up. So this is essentially how long it takes versus one thread, yes. So this was our kind of measure of success, in a sense. We wanted to use these cores as much as we could. There are some data sets, for example, this one here, it turns out that there is not a lot of reasoning there. So, this actually works well when there is actually something interesting to do. Yeah, go ahead.
So there are L and LE. What are the...
Oh, those are just various different versions of the data log program. So, like it's a naming scheme which we introduced in the paper. So I have no time to really go into that.
So by what factor does fact expansion happen?
Well, it also depends. In some cases, you have double, but in some cases, you have an order of magnitude. Well, okay, to get this order of magnitude expansion, that's the LE, it's the extended, that's what E stands for. We developed a bunch of rules which make reasoning much harder. And then, you get this like blow up by factor of 10 or 20 even in some cases. This is simply because these rules encode creation of large cliques. We also compare this with the state of the art. Now, this was a bit difficult because in the state of the art, there is no other system of that form that works in main memory, targets multi-threading, so we couldn't just take whatever. So what we decided to compare it with systems running on a RAM disk, which is not ideal, but the best that we could do, essentially. And implemented using relational databases, and there was this OWLIM Lite, although I think they renamed it into GraphDB recently. That's like a company which specializes in building these kinds of systems and only on a single thread. And I don't have the time to really explain this table in detail, just, you know, the headline message is that it worked really well, as you would imagine, otherwise I wouldn't be telling you all of this. Now, okay, because, you know, we had quite a bit of discussion, I'm going to have to skip some of this presentation. So just maybe very briefly, what you can do is, in RDF, you can say that two resources are equal. So, for example, you can say US and USA is the same thing. And these kinds of things are quite hard. You can still encode them using rules, but what happens then is this encoding using rules essentially copies. So everywhere where you see US, you copy the triple and say, oh, but this also can be USA. And this is, well, you know, this actually leads to the derivation of quite a large number of triples. But the worst thing is actually, it leads to the derivation of the number of derivations that you derive a triple is even higher. It's cubic in this case. So there is this well-known technique of so-called rewriting. I won't be able to run through the example because I'm running late here. Just maybe very briefly, the idea is essentially that when you say, you know, America is the same as USA, then you pick one of these two constants and you replace all the other occurrences of the other constant with one. Now, this has been used quite often in practice in a lot of these systems, but actually, we are, I think, the first to actually make sure that all of this works completely correctly in all the corner cases. And in particular, what we need to do is we need to update the rules as well. So in this particular example has been constructed so that you don't actually get correct results. So you lose completeness, essentially, if you don't update the rules. And that adds a layer of complexity and so on. But as I say, I have no time to now go into the details here. And this is, again, an evaluation that we did. So this is, you know, how long it takes if we do stuff using axiomatization on various numbers of threads. And this is how long it takes if we do it using rewriting. As you can see on quite a lot of, you know, data sets, this rewriting speeds things up quite significantly. But also the question was to ensure good speed up, you know, so that we still effectively use these threads. And that was yet another kind of important aspect of this work. I have no time to go into that. And the final thing which I'd like to just briefly mention is, as you've already mentioned, you do this materialization. It's all there in the database. You run your queries, and then something changes. And then, you know, the idea of, you know, yeah, go ahead.
For the previous, are you saying that the previous implementations would get that example wrong?
Yeah, precisely. And actually, we ran it by them, and it is really wrong, yeah. So, I mean, you know, it's a minor, the contribution is not major. We haven't invented that technique, but, you know, doing it correctly is still involved, basically. And, I mean, we care really about provable correctness. So for all of these algorithms, we have actually a proof that the algorithm works correctly in the face of, you know, parallelization and threading. I mean, then, of course, I make a bug, you know, like I introduce a bug into the software, so the proof is still, you know, just there sitting on my desk, but it's better than nothing, really. This last thing is basically, as you said, you know, we have some data, the data changes, what do we do now? Do we just, you know, throw everything away and start from scratch and wait for hours? Obviously, the answer is no, and people have already looked at that. There is this so-called delete rederive algorithm, which I will briefly outline. This is the only algorithm, to my knowledge, we've actually surveyed the literature quite extensively, the only algorithm which works with recursive rules. I mean, there are solutions which are applicable to non-recursive rules, but they don't work correctly. And our goal was, again, to be, you know, bomb-proof, at least on paper, basically, modular bugs in our software. So how does this DRED algorithm work? So here is a very simple program. And this is my input database. And now, you know, what this essentially does, it says A implies C0, B implies C0, and then these CIs imply each other in a cycle. And this is what materialization looks like. And now let's assume that I want to delete A of A. what the DRED algorithm is going to do, it is going to first delete all facts which have a derivation from A of A. And the way this is done, this algorithm modifies the rules in this way. So it says, if A of x gets deleted, then C0 gets deleted. If B of x gets deleted, then C0 gets deleted. And then for each of these rules here, you get again this version of a rule which essentially says, well, propagate these deletions onward. This is, again, the main problem here is that you can have multiple derivations. Like, so for example, here we have A of x and B of x both imply C0. Okay, and then once when, but this is now incorrect. So at this point, I'm saying just B of A, stays, essentially. What you now have to do is you now have to rederive those facts which stay, essentially. And this is, again, done not quite. This is a very concise way of summarizing what the algorithm does. There are more things there happening under the hood, but I think this is enough to understand the algorithm at a conceptual level. So you say, okay, for all of these facts that were derived, check, whether they are still, that were deleted, check whether they are still derived. And what you then actually do is you now put all those facts back in. Okay, there was an animation missing, so I would now have to remove all these lines basically from C0 to Cn. You had a question?
Yeah, so what if a fact it was already there and it was not derived? So you have to keep track of what was derived and what was initially there, right?
You have to keep track. You can delete only stuff which was there in the beginning. There is a whole different area of research which tries to delete derived facts, but there the semantics is not clear. So what does this mean? So that's the problems there are not efficiency of how we do this. They are, but there is yet another problem, like what does it all mean in the first place? We actually don't address that problem. We address the problem of just delete the explicit facts. This is a problem, and actually the problem is that in the semantic web, facts actually tend to have quite a lot of different derivations. Simply because of the way these ontologies are constructed, these rules are quite redundant. The number of derivations is in the billions, whereas the number of facts that you derive are in the low millions, for example. So because of that, actually, you really get this huge blow up in the number of derivations, and this algorithm tends to be quite inefficient because you quite often trash, sometimes we saw examples where you trash the half of the database, basically, in order to actually rederive it later. So we clearly don't want that. And we developed a new algorithm, which we call the backward-forward algorithm. So again, I won't present everything, but just the rough idea is, okay, we again want to delete this A of A. So now, just like in the DRED algorithm, we essentially identify facts which are derivable from A of A. But then we say, okay, question mark, is this fact still derivable? Well, okay, we now look through the rules and say, okay, this fact can be derived by this rule. So let's now go backwards and check B of A. B of A is still there. I haven't derived it, so that guy stays. But then C of A stays as well. And I'm done. Because C0 of A stays, I don't actually go on to propagate stuff across this big circular chain. This gets much more complicated because of a variety of reasons, which I don't have the time to go into. So there is this backward and forward step, but you'll have to read the paper. I hope it gets accepted. It's currently under submission. Go ahead.
Should there be a step 0 checking if A of A is derivable?
I'm sorry?
Should there be a step at the very top checking that if A of A is actually derivable?
No, because you've deleted it explicitly. Well, yeah, I guess it would be, yes. Yes. I should have maybe said that. Check whether it is derivable, but there is no rule which derives it. Yeah, okay, you're right. Yes, there would be. I didn't think about it when I wrote the presentation. And the conclusion, this is a main memory system, and what we'd like to do is obviously use the memory more efficiently. Now, for that, we would need to use some kind of data compression. This is a bit more difficult. We had a very efficient data structure for compressing this RDF data, but the problem there is that we used variable encoding, variable length encoding for various parts of these tables. And that is a problem simply because these write instructions are guaranteed to be atomic only in most processors, only if you're aligned to word boundary, basically. Now, this is quite difficult then, to ensure atomicity even if your data is not aligned. So then we just basically dropped that. And maybe we'll get to this at some point as well. Another thing is, so far I talked only about reasoning, and this was our main focus so far. But this system also supports querying. And there, it could be better, simply because, as you, I'm sure all know, there is this notion of query planning. So when you get a query, you want to find the plan, which is most efficient. We currently use a very simple, simplistic algorithm for that. But we have some ideas on how to improve this using some theoretical results on bounded hypertree-width. And then another thing is, so to do this planning, you need what you call joint cardinality estimation. So you have some order of your atoms, and you want to know roughly how many triples will this produce. Now, in databases, usually they do this by sampling the data, using one-dimensional distributions, and then making what they call variable argument independence assumption, which essentially means that if you have an n-ary relation, then all of these n columns are somehow statistically independent from each other. Now, in a database, this may not be such a big problem because you have lots of different columns, and lots of different tables, and but in here you have just one table, the triple table. And doing this variable independence assumption, it doesn't really work. So I've got some ideas on how to do this using n-dimensional histograms. But then the problem is basically your query estimation procedure now becomes exponential in the number of variables. But I have got some idea, again, how to apply some theoretical results to reduce that. So we'll see. Keep, watch this space. Thank you very much.
I guess you got no time.